Imagine living in a universe that extends far beyond the boundaries of our familiar three-dimensional world. Deep within the fabric of reality, scientists envision a hidden realm, a warped, fifth-dimensional space waiting to be explored, where the forces of gravity and electromagnetism converge, merging in a breathtaking dance in this domain. How do we access this mystic realm through the supposed portal? Through a hypothetical particle. A cosmic portal can travel across the vast expanse of the cosmos, bridging the gap between the known visible matter and the elusive dark matter that hides the universe in its mysterious secrets. The concept of a five-dimensional space existing beyond the four dimensions of time, commonly used in relativistic physics, has long been a fascinating and scary topic. Back in 1921, the visionary minds of German mathematician Theodor Kaluza and Swedish physicist Oskar Klein introduced the Kaluza-Klein theory, independently proposing the presence of a fifth dimension to unite electromagnetic force and gravity. Klein even theorized that this fifth dimension might be compacted into a tiny loop hidden from direct observation. However, as the 20th century unfolded, further research uncovered the flaws in these early approaches, as scientists of that era held contrasting views on the existence of a fifth dimension. Fast forward to the 21st century, and a fresh wave of scientific inquiry has reignited interest in possibly reaching this dimension through the possible portal of hypothetical particles. A group of esteemed researchers, Javier Castellano, Matthias Neuber, and Adrian Carmona, made a discovery in their study, published in the European Physical Journal. These brilliant minds present a compelling model of the universe featuring a fifth dimension attainable through a portal formed by particles. Their work delved into the intricate complexities of this hypothetical realm, shedding light on the fundamental mysteries that encompass the journey into the fifth dimension. As the study reveals, these speculative particles may hold the key to unraveling the mystery of dark matter, a mysterious substance that penetrates the cosmos, making up most of its mass, yet remaining unidentified. The researchers suggest that these particles provide a natural explanation for the abundance of dark matter, offering a solution to the perplexing puzzle surrounding subatomic particles known as fermions. The scientists who took part in the study gave the public a glimpse into their inspirations and driving forces in an email to Vice. The scientific team has also been looking into the possibility of a four-dimensional space that humans can easily relate to. The fourth dimension is three-dimensional space and time, and scientists have been surprised at how we can gain access to this dimension. While many people believe that the universe can only provide fourth-dimensional space, many scientists believe that we can access more dimensions like the fifth dimension. To grasp the inner workings of this fifth-dimensional portal, let us dive deeper into the theoretical model known as the Warped Extra Dimension, WED. The WED model introduces a curved fifth dimension, influencing the behavior and interactions of particles in profound ways. Among these particles is a scalar that is very similar to the famous Higgs boson and is responsible for giving mass to other particles. Yet, unlike the Higgs boson particle observed by the Large Hadron Collider in 2012, this scalar particle is too heavy for the current collider's capabilities. To understand this WED model, picture a universe molded by warped geometry, where the very fabric of existence is made up of a five-dimensional anti-de Sitter space, ADS5. This design gives the fifth dimension a negative curvature, similar to a slice of a hyperboloid. This curvature is also coupled with an energy scale associated with each point along the fifth dimension, which decreases exponentially as we move away from a reference point. Within the WED model, two borders, or branes, span the fifth dimension, one at each end. These branes manifest as four-dimensional subspaces, providing a home for fields and particles to localize. The UV brane at one end has a high energy scale, whereas the IR brane at the other end has a low energy scale. The amount of warping in the fifth dimension is determined by the distance between these two branes. Central to the WED model is the KK parity symmetry. heralding the presence of two copies of each field and particle in the fifth-dimensional realm. These copies possess even and odd KK parities, resulting in their respective symmetrical and anti-symmetrical behaviors under reflection along the fifth dimension. As a result, only even KK parity entities can exist on both branes, while odd KK parity entities confine themselves to a single brane. According to the WED model, all standard model fields and particles take the form of even KK parity entities localized on either brane. The degree of localization is determined by the mass of these parities, with lighter counterparts gravitating near the UV brane and heavier counterparts congregating near the IR brane. This localization mechanism explains the hierarchy of fermion masses and CKM mixing angles with their placements along the fifth dimension, reflecting their distinguishing features. This localization also becomes a protective shield against flavor-changing neutral currents, effectively suppressing them due to limited overlap throughout the fifth dimension. The intriguing notion of an unusual KK parity field that seamlessly spans both branes, the scalar field that serves as the portal to the fifth dimension, is within the WED model. Because of its potential, the scalar field has a non-trivial profile along the fifth dimension. There are two sources of this potential: bulk dynamics and brane dynamics. The bulk dynamics stabilize the extra dimension size by creating a powerful tension between the branes, and the brane dynamics add mass to the scalar field and associated KK excitations by breaking its shift symmetry. The scalar field can couple with both even and odd KK parity fields via its kinetic term or brane-localized interactions. The scalar field can use these couplings to mediate between visible matter on one brane and dark matter on the other. Dark matter, which consists of odd KK parity fermions in the bulk, has masses based on their boundary conditions along the fifth dimension. However, scientists remain hopeful, searching for indirect evidence of the existence of the scalar particle and investigating its potential impact on the universe's early history and the gravitational waves it may have unleashed. These gravitational waves, cosmic ripples triggered by cataclysmic events such as black hole collisions and neutron star mergers, can be detected by sophisticated instruments like Virgo and LIGO. These instruments have already captured several interesting gravitational wave signals since 2015. If the scalar indeed exists, it has the potential to unlock secrets of dark matter, with its gravitational influence on galaxies and celestial structures serving as a telltale sign. Dark matter is believed to consist of fundamental particles dwelling within the fifth dimension, interacting with ordinary matter through the gateway provided by the scalar. Also, the scalar field particle interacts with the Higgs field via mutual potential, having a significant impact on the Higgs mass, couplings, and even initiating decay channels for the scalar field into standard model particles. The complicated interplay alters the environment of electroweak symmetry breaking, transforming the Higgs potential into a dynamic force. The scalar field particle has an extensive list of fascinating phenomenological implications. It has the power to shape the universe's evolution during its early stages, leaving an indelible stamp on inflation, baryogenesis, and reheating processes in the field of cosmology. In astrophysics, the scalar field particle leaves its mark on the formation and distribution of dark matter structures, impacting death, decay, and scattering processes. Finally, the scalar field ushers in a new age of possible signals at high-energy colliders, influencing the creation, decay, and detection processes of standard model particles and associated KK excitations. Gravitational waves are one of the most promising pathways for putting the WED model to the test and discovering scalar field particles. These waves provide yet another manifestation of odd KK parity fields spanning both branes as the metric tensor fluctuations that ripple along the fifth dimension. Their masses are determined by the boundary conditions that they meet. The WED model has multiple sources that generate the gravitational waves, ranging from inflation-driven primordial waves with a specific spectrum to phase transition-generated stochastic waves with distinct properties. Radion oscillations can also produce monochromatic gravitational waves with large amplitudes. Numerous detectors on Earth and in space are looking to detect these gravitational waves. The LIGO and Virgo detectors, which are tuned to frequencies of about 100 Hz, have already captured the reverberations of these cosmic waves, ushering in a new era of discovery. The LISA detector, designed to detect gravitational waves at frequencies around 10 to the -3 Hz, and the PTA detector, aim to detect waves at frequencies around 10 to the -9 Hz, stand as beacons of hope in the search for cosmic enlightenment. Through the properties and interactions of the scalar and its entanglement with other particles, scientists can glean invaluable insights into the nature, origin, and cosmic significance of the dark matter, ultimately unraveling the very fabric that shapes our universe. A discovery as monumental as a portal to the fifth dimension would revolutionize the fields of physics and cosmology, opening doors to possibilities for exploring and understanding the profound mysteries underlying the fundamental nature of reality. Such a breakthrough would challenge our perceptions of space and time, igniting our imaginations to soar beyond the walls of our four-dimensional world, envisioning the infinite wonders that lie beyond. The more information is gathered on the possibility of the existence of a portal to the fifth dimension, the more mysterious it becomes. Its discovery would defy human knowledge, ushering in a new era of inquiry and comprehension. It could ultimately solve the mystery of dark matter, revealing the invisible forces that create our universe. Prepare for the portal to the fifth dimension, which opens up a realm of unlimited possibilities and invites us to question our very existence in this awe-inspiring fabric of space and time. And that brings us to the end of this video. Do you also think that a portal to the fifth dimension exists? Let us know if you enjoyed this video. And as always, keep exploring.